Hi there, welcome back. Uh, we've recently been talking about polar coordinates, polar equations, polar inequalities, polar curves, and what we're going to do now is we're going to switch our focus back to double integration, and we're going to use these new tools that we gained by thinking in a polar fashion to be able to calculate double integrals of a function over a domain when the region is better represented with polar inequalities. So, for example, we can talk about circles centered at the origin. When you have your domain that looks like a circle centered at the origin, that's a key that we'll probably be thinking about calculating that integral using polar coordinates. Another example, polar rectangles. Whenever you have some part of an annulus, that's another type of region that's better represented with polar inequalities. Also, regions between two polar curves. We saw these when we were trying to calculate the area uh, of this region, but you could imagine that we might want to take the integral of a function over this region, or for example, find the center of mass of a region that looks like this. These are the different types of regions that we will now be able to integrate over because of the new skills and new knowledge that we have from a polar region point of view. The other time that we might be trying to use double integrals over polar coordinates is when this involves functions f sub xy that would be better written as a function of r and theta. And we'll see some examples of this later, but one clue that you might have that is that f of xy seems to have a lot of x squared plus y squareds in it. And having x squared plus y squared, we know, is the same as having an r squared. So that may end up helping us simplify our calculations. So this is our goal. Our goal is to be able to calculate these double integrals when we have a domain that maybe we wouldn't be able to calculate otherwise, except if we convert over to polar coordinates. All right, so how do we do this? What are the steps to be able to convert this integral? So, I mean, we have to be careful. If you look at this, this was a function in terms of x and y. We're not in the land of thinking of our function as a function of r and or r as a function of theta anymore. We're still thinking of this function f as a function of x and y. But what we're going to do is we're going to convert this over to an integral that has some thetas in it, some r's and thetas in it. And so we need to talk about how do we get from xy land over to r and theta land. All right, so the first thing that is really important to understand is that the idea of dA, so when we're calculating the integral of f dA, this dA before, we were using dA was equal to dx times dy, because when you have a region and you slice it up in terms of x's and you slice it up in terms of y's, then the little piece of area is a dx times a dy. When you're dealing with slices, so if we looked at this same region, but instead we sliced it up in terms of r's and thetas, well, remember d thetas now are these angle slices, and we have dRs are now these radial slices. So now the question mark is, how can we write down an expression for what dA is if we have some angle? So let me highlight it with a different color. We have some angle here, d theta, and then we have some radial change dr. So now the question is, what is dA equal to in terms of dr and d theta? So we've seen something similar to this before. The key aspect of this is when you're out here at a distance r from the origin, since d theta is an angle, this distance of this little tiny slice is r d theta, whereas this is dr. So in fact, dA in this regime is no longer equal to dx dy, it's r dr d theta. Okay, and so I like to make the joke that polar coordinates aren't actually polar coordinates, they're pirate coordinates. Because instead of writing dx dy, you write r d theta, right? So you should practice saying that in your head, r d theta. So whenever we're starting here with an integral, that's we have the integral of f of xy dA, we want to convert it into an integral in terms of r and theta. Then what we get is we get this integral over our domain of f of x, which is r cosine of theta, y is r of sine theta, and the dA becomes r d theta. Okay, so whenever you, so what in words, what we have to say is that to calculate the double integral of d over d of f of xy dA, when d is best described in polar coordinates, you calculate this double integral over our domain of f of r cosine theta, r sine theta, times r d theta. All right, so let's do an example of this. So let's see. So let's find the area inside r equals 4 cosine of theta from theta equals pi over 4 to theta equals pi over 2. All right, so at first glance, this looks exactly like one of those equations that we did before, which is to say, okay, so we have our 4 cosine theta, we have theta equals pi over 4, theta equals pi over 2, and we're looking for this area. So we're going to take this and turn it into a volume question by taking this, turning it on its side, right, and saying, all right, so this is our domain. Our domain is this piece right here, and we're going to say that our function f of xy is equal to 1. So we're basically building a cylinder of height 1 over our domain. And then the volume of this is going to be equal to the integral of 1 dA. So this is our height, and this is our area. And so that's how we can turn this question, that's an area question, into a double integral question, as we've done before. So this 1 dA, because we're in polar land, this 1 dA becomes 1 times r dr d theta. And the key aspect of this is writing down our domain in terms of polar equations. So now the key becomes to write D as polar equations. Right, and so just as we've done in the past, where you need to draw your slice. Here we're drawing a slice, and our slices start slicing at pi over 4, and they stop slicing at pi over 2. And what's the lower bound and the upper bound of these slices? Well, the lower bound is 0. This is r is equal to 0, that function. And the upper bound here is r is equal to 4 cosine of theta. All right, and so what that means is if we're writing down our double integral, we're going to start slicing at theta is equal to pi over 4, keep slicing until theta is equal to pi over 2, and then r is going to go from 0 up to 4 cosine of theta. And then we need to integrate just the function 1 dA, which we know is equal to r dr d theta. All right, so let's do those steps. As we integrate this, we get the integral from 0, theta is equal to pi over 4, theta is equal to pi over 2 of r squared over 2 evaluated from 0 to 4 cosine of theta d theta. So this gives us an integral from theta is equal to pi over 4 to pi over 2 of 4 cosine of theta squared over 2 minus 0 squared over 2 d theta. All right, so now what do we have? We have 4 squared, 16 divided by 2. We have the integral theta pi over 4 to pi over 2 of 8 cosine squared theta. We again need to use our trigonometric identity. So cosine squared theta is equal to 1 plus cosine of 2 theta over 2. So this integral becomes theta is pi over 4 to pi over 2 of 4 times 1 plus cosine of 2 theta d theta. So now we integrate 4 theta plus 2 cosine of 2 theta, 2 sine of 2 theta, evaluated from pi over 4 to pi over 2. And so in the end, what do we get? We get 4 times pi over 2 minus pi over 4, plus 2 times sine of pi minus sine of pi over 2. And so we get pi minus 2, pi minus 2. And so the area of that slice is exactly equal to pi over 2. Sorry, pi minus 2. The area here is pi minus 2. Before I stop for today, what I wanted to do was highlight this line of our code, this line of our work. If you look at what happened, we said our little dA was equal to r dr d theta. When you take the integral of that with respect to r, what do we get? We get r squared over 2. That's exactly what we had in that previous and the last thing that we've been talking about, which is just finding the area where we had r as a function of theta. We had to do the integral of r squared over 2 d theta. So you should look at this equation that we had, this area equation, and you should just recognize, hey, that's exactly the same thing that we had before, just written now as a function of r and theta instead of just a function of theta. All right, so that's it for today. I will see you later. Bye.